Welcome back to Tracing the Sky. I hope you're enjoying our series on Aristarchus so far, and I hope you can also see why he's one of my favorite astronomers. When you look at his journey, you really get an appreciation for how incredible the human mind is and how powerful certain principles are. You can see what we've done so far with circles and triangles. Just knowing a little bit of geometry and some of their principles and properties allow you to solve problems close to Earth, but also at seemingly insurmountable distances. And so today we're going to continue that journey and look at his next discovery. So let's have a look at my screen and take our next step. Okay, so here's a little summary of what Aristarchus discovered last time, or how he started to imagine things. Remember, the circumference of this circle is the moon's orbit, right? He's thinking about the moon's orbit as this circle around the Earth, and its circumference is this perimeter here. The distance from the center of the Earth to the moon is also the radius of this circle. We also learned last time that there's a relationship between the radius of a circle and its circumference. It's 2 pi r, right? The circumference of a circle is equal to 2 times pi times r. And so we could rewrite this as the size of the moon's orbit, right? That circumference is equal to 2 pi times r, but in this case, instead of writing r, we can just write the distance to the moon. Now, what I want to just be really clear on is that the distance to the moon is the radius. It's just another way of describing what the radius means in this particular situation. And so Aristarchus starts wondering if he could measure the distance across the moon, right? That's the diameter of the moon. Remember, radius is from the center of the circle out, and diameter is just all across, going through the center. If he can measure the diameter of the moon and then stack a bunch of moons around the entire circle, can he create a relationship between the size of the moon's orbit, right, the circumference, and the distance to the moon? Because then that will allow him to simplify his problem. He wants to figure out the distance to the moon and the size of the moon. So if he can create a relationship, then that might help simplify things. And so he's essentially trying to ask and answer the question, how many moons are there in the orbit or in the circumference? If I were to stack the moons, how many of there would there be per each circumference? And if he can figure that out, then he can create a really interesting relationship. So let's look at how he solves this next step in the problem. Okay, so Aristarchus wants to relate the size of the moon to the size of the orbit. Now, he doesn't yet know the exact size in terms of like meters or feet. That's ultimately what he wants to try and find out. The distance to the moon and the size of the moon in one of those kind of conventional distance measurements, like how many miles to the moon or how many miles across is it? So what is he going to do? Well, he wants to relate their two sizes. So he doesn't need to know the exact size. He just needs something that he can do to relate how big is the moon to how big is its orbit. And another way to think about this is how many moons can you fit in the orbit? If you stacked all the moons together, how many would fit in that circumference? And so here's what he does. He measures the angular distance, right? You can think about it like this. If I were to look at the moon from a position on Earth, right, and I look at one side of the moon like this, and then I measure the amount of turning. So I measure the amount I turn from here to look at the other side of the moon. How big is that angle? What is that amount of turning that I've done? Here, I'll just label so you get a clear idea. This angle here. What is this angle here? So that's what he's trying to measure. He's trying to measure the amount of turning from one side of the moon to the other side. And that's something he can definitely do. There's a variety of ways that you could do this. And so one way, for example, is to measure the coordinate here, measure the coordinate here and calculate that. It's a bit of a complicated formula. But ultimately, all he cares about is that angle. How much turning are you doing from one side of the moon to the other? And he gets that the value is about half a degree. So when you measure the moon in the sky, it's about half a degree across. So for our purposes, we'll round it to half a degree. So the moon, the angular size of the moon, is measured as a half degree. So what can Aristarchus do with this information? Okay, so how can you use this information? Well, remember, he cares about stacking all of these moons and figuring how many of them fit in the orbit of the moon, right? How many of them fit in this circumference? Well, he now knows that a moon is half a degree across, right? If you measure the moon from Earth, right, from Earth, as it appears to us from Earth at this distance away from Earth, it's about half a degree across. Well, if you were to take two moons, that would make 1 degree, right? So if you were to stack two moons together and measure the amount of turning from one side of the first moon to the second side of the other moon, let's just draw that here. So if I drew another line here to the edge of the second moon, that angle, that amount of angular turning would be a single degree. Well, how many degrees are there in a circle? You've probably learned this before. There are 360 degrees in a circle. So if there's two moons for every 1 degree, that means there are 720 moons in this circle, in this orbit. So if you stack the moon all the way around the orbit of the moon, you would have to put 720. There would be 720 moons to one circumference, to the moon's orbit. So now he can plug that into his formula and start to see a relationship. Let's do that next. Okay, so let's see how he applies this, right? Remember, the circumference of a circle, any circle, is equal to 2 times pi times the radius of that circle. And so when you know that relationship, you can solve for either one. If you know the radius, you can multiply it by 2 n times pi and get the circumference. If you know the circumference and you want to figure out the radius, you can divide it by 2 and then divide that by pi and get the radius. So that's why this sort of thing is powerful. When you establish a relationship like this, if you know one thing, you can calculate the other thing. And so then remember, we just swapped out some of these things, right? Circumference is actually the same thing as the size of this orbit. That's what we're talking about here. The moon's orbit here is the circumference of this circle. And then we said the radius is just the distance to the moon. That's this red line here. That's the distance from the center, from the Earth, to the moon. That's the radius. And so we could rewrite things to say, well, the size of the orbit, that circumference, is equal to 2 times pi, then the distance to the moon. And then we said that, well, wait a second. If each moon diameter is half a degree, then there are 2 moons to every degree, and there are 360 degrees in a circle. Therefore, there are 720 moons to every moon orbit. So the circumference of this circle, the moon's orbit, is the same as 720 moon diameters. And notice how I'm just taking this and I'm swapping it here. If these two things are equivalent, right, then I can replace size of moon orbit with 720 moon diameters in my function. And so now in this formula here, I can say that there are 720 moon diameters, and that is equivalent to 2 times pi to the distance of the moon. And so look how incredible this is. If I can figure out the distance to the moon, right, and I multiply it by 2 times pi, and then I divide it by 720, I can get the moon diameters. So I hope you're following along with this. It's a lot of algebra and jumping around, but this is the same as any other algebra you would have learned when you're solving for X or solving for Y. So if you are using this with students, I would recommend that they're comfortable with algebra, right? Instead of saying X and Y, we're just saying moon diameters or distances to the moon. You could also rewrite this as moon diameters as X and distance to the moon as Y, and you would solve it in the same way. So this is hugely powerful. Like I said, if he has the distance to the moon, he can calculate the diameter of the moon, and vice versa. If he figures out the moon diameter, he can then calculate the distance to the moon, right? He can multiply it by 720, then he can divide it by 2 and divide it by pi, and he'll know the distance to the moon. So think about how far we've come. Aristarchus started by saying, how big is the moon, how big is the sun, and how far away are each of them? And he had no information. He didn't know where to start. He didn't know anything about them, right? About how far or how big they were. And look how far we've come. He knows a relationship between the sun and the earth and the moon, right? He knows how much bigger the sun is than the moon. He thinks it's 19 times, right? And he thinks it's 19 times further away. So now he can focus on the moon. He doesn't need to worry about the sun right now. Now he focuses on the moon, and he doesn't know how far away it is. And that's the next thing he wants to figure out. And so now he eliminates another thing. Now he doesn't need to figure out both things. He just either needs to figure out the distance to the moon or its diameter, and then he can solve the other one. If he gets the diameter of the moon, he can figure out its distance. And once he knows that, he can solve the sun. He can just multiply it by 19. And so look how far he's come, just using some simple geometric devices, some really incredible creativity and imagination, and, a lot of genius on his part, right? The genius is his ability to even think of these things. So in the next episode, we're going to look at how he figures out one of these values. He's going to actually turn his attention to the diameter of the moon. He's going to see if he can figure out the diameter of the moon using something really, really clever and simple. So join me next time, and we'll see how Aristarchus starts to figure out how big the moon actually is. Join me next time.